Hello everyone, I'm Yakshit from hadl batch. I will be discussing about my project performance analysis on flash attention on NVIDIA 88GB GPU. The primary aim of this project is to address the scalability limitation of the standard transformer attention mechanism, which suffers from the quadratic memory complexity with respect to sequence length. So this complexity creates a significant bottleneck neck, preventing the process of long sequence and limiting the performance of large-scale models. So we are trying to implement one of the mechanisms of flash attention which is used to do this complex calculation of the attention formula in a much simpler manner. And we'll try to plot the graph between the flash attention effectiveness and the py dodge attention using the T flip-flops consideration. And yes, we will be analyzing about the speed, memory, efficiency, scalability and GPU utilization of various configurations. So let me discuss about the algorithm that we will be using. So the flash attention mechanism depends on the algorithm as follows. So the standard scale product attention goes with the formula attention of the Q kV is equal to the softmax of Q into K transpose divided by under root of dk multiplied by V, where small q kV are the query and the value, whereas the dq was the sequence length on which this computation depends quadratically. So the main bottleneck of this process is the large attention matrix, which consumes memory and slow down the computation due to extensive read-write operation to the GPU's high bandwidth memory, that is HBM. Now the flash attention overcomes this limitation by IO aware, meaning it optimizes data movement between the GPU's HBM and it is much faster on a chip SRAM. So as we all know, the GPU HBM has a huge memory, but it is very slow as it is far from the one main computation unit. Whereas the SRAM has very less memory in KVs, but it is very close to the one, so it will take very less time. So how we will be doing this huge calculation in these three processes? First is tiling will break down the input matrix into smaller blocks, and these blocks will be loaded into the fast SRAM where the attention compression happens. Then we'll do the all-line softmax, as in the length of the softmax is done incremental on each block without needing the complete matrix, and it maintains the statistic normalization. Then the recomputation at the end, after getting the each block value, we will recompute with the softmax function so that we get the final value. Discussing about the thing that we are using fusing here, the CUDA kernel flat attention basically minimizes the memory read-write operation, leading to the linear usage. From a quadratic we came to lean. Now the benchmark implementations will happen with respect to the standard PyTorch attention. As we all know, it's a direct implementation which gives a quadratic memory complexity and performance limitation. Xformer is a library that is developed by Meta AI, and it is highly optimized for the transformer model. It's also trying to do the same, but we'll see how our model outperforms this. Then the flash attention, which is written in Triton, as Triton is a Python based language that enables researchers to write highly efficient GPU kernels without needing to write low level CUDA codes. The last is flash attention 2, that is based on the CUDA directly writing into a CUDA. Before that, let's get into discuss about the attention pattern, the casual and non-casual. Non-casual is a bidirectional attention, so via the token can see the tokens itself.
Sure.
The before tokens as well as the future tokens. So whereas these are used in the encoder models like BET model, type sentimental assets, etc. Whereas the casual is the mass self-retention, where the token only sees itself, and the past tokens that is unable to see future tokens. So it is unidirectional, or it is used in the autoregressive or text generator, as we generate the text based on the previous text. These are used in like ChatGPT you can understood that here the casual attention mask is a why memory efficient implementation of flash in attention provide a even greater speed up and in this mod compared to the non-casual. So when we get into the code, we understand that we have implemented the PyTorch attention implementation by iterating to various configurations. And yes, this script is content implementation. I'll be sharing the screen right now. So we have first maintained our environment of the A880 GPU with a locked container. So you can see the script here. So yes, this is the script. This is the benchmark mechanism script where you can see that we have things like, let me show from the start. Yep, these are the imported libraries. These are traditional testing libraries. These are time taken just for warm up thing. Then comes the C flops calculation where we calculate the number of flops required. So you can see how here how the flop is calculated. We have taken a window size as it's above the block thing rather than a full matrix computation. And comes the QDOT type where we will convert the type to a PyTorch float type. So we want a float type for the decimal ones and the integer. On the floor 16 in the sense 16 bit, 32 means 32 bits. Then comes QKV casual ones. Here we taking the casuals as flop false, and as you can see here we have the multiple values. Let me show you. Yeah, here's the formula that we have written. As you can see, attention scale is 1 by root dk, and these head dimensions are generally taken as 128 or 64 in our implementation, and the other values as taken as shown here. So here you can see, I guess we talked about that we drop out casually in is false type sequence length. We are varying from 128, then 512, then 2048, and the head dimensions are 256. These are all just commented as I tried each at a time. It's a single script that runs on the multiple conversions. As you can see, we have benchmark backward as well as forwards. The both resides in the training, and let me show you the plot here. You can see these are the non-casual values. These are the T flip-flops have been used. So we systematically working on the OOM that is out of memory bound that happens when you go for a very high length sequence, and you have a 8 GB memory but you are going to use more than that. This error happens. So first let me show you. I'll show you this testing working. Let's see this goes how I come across these values with non versus casual. These are the values for the PyTorch on the Transformer, Flash 1, Flash 2, and these are the sequences I have discussed. So running this test script takes a lot of time actually, so I'll be showing if you output. Let me stop the script. I already tried it before, so output looks like something this. I guess it started running. So yeah, so you can see this thing is running. It is conceived. Yes, it's running. So let's stop at some point and understand what it looks like. This is the implementation of PyTorch DQ and KV. So DQ is nothing but the query small difference. How much is coming on the Q difference value? Difference, as you can see, it goes. The script runs, so it takes some time to complete. I can stop it now. So I guess you got an idea. So as you can see here, this may got paused in this much, and we have interpreted it manually. So because it takes a lot of time to complete, and that's how we got these values. So at the end of the script, when we will get the attention, this values, this T flip-flops value as well. Now how we are doing this plot. Yes, we have a plot function. This is the plot mapping. So we're creating plots like this, and when we run this one, we get the plots like this. Let me show you. This is got saved underscore 2. So this is underscore 2 how the plot looks like. As you can see, this plot looks like. So the T flip-flops compared to the size of this flash one attention to, and the highest T flip-flops whereas the lowest is the pi torch, as it uses the conventional method. So same goes with the casual, and as you can see purple is the highest in all of them. That's why we're trying to show, and let me show you one more important analysis that you understand. So this is how many times this got increased. As you can see, it goes from PyTorch casual one increased 9 times, whereas and for non-casual increased the 3 times. So that's how what I said about the single direction bidirectional. As you can see, this is infinite as we go like here out of memory bomb. So this output looks like when I run this script is something like, so it takes some time to run. So let's see if I have my previous running. So this is my GPU consideration like it's been discussed. Let me check through this one if I have output. Yeah, this is the output, looks like sequence length, the flash value, this value. Let me run this one. This is the one as I have discussed. So that's it from my side. I included the graphs code in code as well. This is the idea we implemented to increase the fastness, as our course is more about the hardware optimization as well. So thank you so much.